Okay, yeah, thanks very much, Venkata, for the introduction, and thanks everyone for coming. So yeah, this is a survey on this growing area of adversarially robust streaming algorithms. And I'd like to take questions during the talk. So if you have any, please stop me or ask in the chat box. So yeah, let me first define the streaming model, which is a fairly old model now. So this is a model for capturing very large data sets. For example, internet traffic, streams of financial transactions, data collected from sensor networks, and so on. And typically, you want a single pass over these large data sets. It's very expensive, or in some cases, like network traffic, impossible to make more than one pass. And you also want very low memory algorithms. Okay, you can't afford to store the stream, for example. So formally, we can model this by a stream of poly-n updates to a large vector x. Okay, so x is going to be our underlying vector. It's going to be n-dimensional. And we're also going to assume, just for simplicity of notation, that the stream also has length, some polynomial in n. Okay. And the way the streaming model works is you have a sequence of times t, and at time t, you receive an update, which is a pair I sub t comma delta t. I sub t is a coordinate between 1 and n, and delta t is a change. And what this means is that your new value of the ith coordinate of x is the old value plus this change delta t. Okay, so this underlying vector is undergoing additive updates to its coordinates. And there are special cases of this model. For example, if all the changes delta t are non-negative, this is often called the insertion-only model. And typically algorithms in this model, they store a small sketch or summary of the data, which is easy to maintain under these additive updates to this underlying vector x. This small summary or sketch is much smaller than n bits, okay, which is roughly the space it would take to store the entire vector explicitly. And what you would like in typical applications is that at any point in time, the algorithm can compute or approximate some function f of the underlying vector x using small space. Okay, and some classical functions that are considered in this model are the second frequency moment, denoted f sub 2, which is just the squared Euclidean norm of this underlying vector x, okay, the sum of squares of its entries. Another commonly studied problem is f0, which is the number of coordinates I that are not equal to 0. Okay, it's the support size of this vector x. If you're in this insertion-only model, then this actually is just the number of distinct elements that you see, okay, because each element you see corresponds to an update to some coordinate. So this would just be the number of distinct coordinates that you see. Very well-studied problem. And for those of you who haven't looked at the streaming model much at all, let me just cover one example streaming problem, which is this F2 estimation problem, okay? As I said in this model, you don't want space that is proportional to the length of your underlying vector. And so to get significantly sublinear space, you typically settle for randomized approximation. And for the F2 problem, the usual notion of approximation is to output an estimate F2 tilde, which is within a multiplicative 1 plus or minus epsilon of the actual F2 value, okay, the sum of squares of entries. And the algorithm in the stream is very simple. So what you do is you choose a random matrix S at the beginning of the stream. S is a very wide and fat matrix, so sort of short and wide matrix. The number of rows of S is something like 1 over epsilon squared. The number of columns is n. And this matrix is just a matrix where the entries are random. In each entry is either minus epsilon or epsilon. Okay, I drew it as epsilon times a sign matrix. All the entries are 1 or minus 1. And in fact, the entries don't need to be fully independent. They can be drawn from a limited independent hash function family, which is important for streaming algorithms because then you can store S succinctly just by storing this small seed for a hash function. And the streaming algorithm is very simple. So you just compute S times X in a stream. You maintain the matrix vector product S times X. And this is easy to maintain under additive updates to the coordinates of X, because if you change the ith coordinate by adding the value delta t, if you look at what happens to the sketch S times X, well, it's the old value of the sketch S times X plus the ith column of the sketch. Here's the ith column, and it gets scaled by delta t. Okay, so it's very easy to maintain under additive updates. You know, I see it delta t in the stream, and all I do is I add the ith column of S times delta t to my sketch. And how do you prove, or what do you do with this sketch, and how do you prove that what you do works? Well, the natural thing to do is just to output the Euclidean norm of the sketch, or the squared Euclidean norm, S times X, as your estimate to the squared Euclidean norm of the original vector X. Okay, and you can show that with this sketching matrix S, that it's an unbiased estimator. That is, the expected squared Euclidean norm is the actual squared Euclidean norm. And the variance you can show is at most epsilon squared times the square of the expectation. Okay, so by Chebyshev's inequality, you get a constant, with constant probability, you get a 1 plus or minus epsilon approximation. And yeah, the memory is very good. So all you're doing is maintaining this matrix S, which is actually order log n bits, just to maintain this short pseudo-random seed. And order log n over epsilon squared bits of memory. Why? Because you have 1 over epsilon squared coordinates of S times X, and each coordinate needs a counter with log n bits. Okay? We're going to assume that the updates delta t in the stream are order log n bit integers. Okay, so the entries can be stored with order log n bits. Okay, so yeah, again, please stop me at any time. That's F2 estimation in a stream. Now, you could also ask for what's called a tracking algorithm, which is that you typically want, or I don't know if typically, but often you want that to output an accurate estimation at every point in the stream. Okay, so if xt denotes the underlying stream vector after receiving the first t stream updates, you would like to output a response r of t at that time, which is within 1 plus or minus epsilon of the function value you're computing. Okay, so for example, F2. So you want this to hold at every single time. And if you have an algorithm that works for one particular time, it's straightforward to get an algorithm that works for every time in your stream just by repeating it independently a small number of times, order log n times, and outputting the median estimate of your repetitions. This will give you a very high probability estimate, and then you can union bound for being correct at all points in the stream. That's one naive way of converting an algorithm that's correct at one point in time to an algorithm that's correct at all times. But for specific problems, there are other ways of doing that that often give you better space complexity. Okay, so yeah, the model for streaming that was studied for many years is that you have this streaming algorithm over here that's receiving these stream updates. This server here, whatever it is providing stream updates, and you're outputting these responses at each time. But importantly, that this server doesn't see your responses, okay? So its choice of stream that it's going to feed the algorithm is chosen in advance of your responses, which is useful in some settings, but maybe it's not useful in other settings, okay? So this is the model that the stream is fixed beforehand, and the stream doesn't get to adapt based on your responses. And this is not good in some settings, okay? And this motivates the notion of adversarial streams that I'm going to talk about, okay? So as I said, in classic streams, the data is fixed before the algorithm starts, and future data does not depend on the outputs, RT. But you can imagine if you have a sequence of stock transactions, maybe you monitor it and you make your own stock purchases, and this influences future stock transactions, what comes next in the stream. And now suddenly these streaming algorithms have no known guarantees, okay? Because the future updates in the stream depend on the randomness of your underlying sketch that you're using. And once you have that dependence, these correctness proofs no longer hold. This motivates a new game. So in adversarial streams, there's an adversary that controls the stream updates. It sees a response R of t, and it also knows all the previous responses that it's seen, and it uses these to generate its next stream update, the t plus first stream update. Okay. So I can draw the picture again. It's a little bit different now. Here is an adversary on top of the server. It feeds in the first stream update to the streaming algorithm. And now this response of the streaming algorithm, R1, is fed back to the adversary. Okay, the adversary looks at the response, thinks about it a little bit, and then generates its next stream update. Okay, then sees the next stream response, and so on. Okay, generates its next update. So we have a two-player game now. Okay, now we'd ideally like to design algorithms that work for any adversary. So the adversary is not limited in computational power. And we will see that almost all of our algorithms have this property. But in some settings, maybe you want to do even better. And then you could think about maybe polynomial time adversaries and so on. Okay, so what is the goal of the adversary? Well, it's to make the algorithm fail, to output an epsilon approximation. So what does that mean? The adversary wants, for some time step t, that the response rt is not within 1 plus or minus epsilon of the desired function value at time t. Okay, and note that it's determining what xt is, right? It's controlling the underlying stream. And yeah, so for the most part, we're going to assume that the adversary has unbounded computational power, and it knows the entire history of the outputs, R1 through RT minus 1 at time t. Now, there's a natural way of designing adversarially robust streaming algorithms. Well, why don't I just choose a deterministic algorithm, right? That works on all inputs, so it doesn't matter what the adversary chooses. However, most streaming algorithms provably must be randomized, okay? Otherwise, they require a huge amount of memory. And so, yeah, how do we design these algorithms? And this is a real issue because if you look at classical algorithms, for example, this algorithm I described for F2 estimation, it's called the AMS sketch for Alain, Matthias, and Segedi. So that works for estimating F2. I showed that to you guys, but it turns out that it's not adversarially robust, meaning you can completely break it in a stream with only, even in an insertion-only stream, with a very small number of updates. In fact, you only need one adaptive query, and the rest can be non-adaptive. So you can completely break this very classical algorithm, which is sort of bad news. So we need new algorithms. Okay.
So David, do you have an example for this, like this AMS sketch breaks down for?
Yeah. So in the paper we give the intuition. The intuition is roughly, what the AMS sketch is doing is it's outputting the squared norm of s times x. Okay, and these columns they're random, but they're not orthogonal to each other. Oh, sorry, I shouldn't draw them as the same. There's some correlation between them. So maybe two columns are slightly more positively correlated or slightly more negatively correlated. And when I put an update EI, like I add one standard unit vector, and I look at my new L2 norm of the new vector, then what I can kind of do is I can see, well, did it increase, because I get the exact L2 norm, did it increase, a little bit less than it should have or a little bit more than I should have? And by doing that, I know if EI is correlated with things I've already chosen. And so after doing a bunch of non-adaptive queries, then I know which EIs are correlated with each other. And then I can do like one disastrous query where they're all correlated with each other. Yeah, that's the rough. Okay. Yeah. Any other questions? Okay. Yeah, so the main result of this first paper with Ben and Lizier, Jairam, and Yogev was we gave two generic methods to transform any streaming algorithm A into an adversarially robust streaming algorithm A prime with a mild space overhead. Okay, so we call these two generic transformations sketch switching and computation paths. And I'll describe, why they're called this in a moment. Let me just say, these two generic transformations we give, they have pros and cons that are useful in different settings depending on the underlying streaming algorithm that you're using. Okay, so sketch switching is particularly useful if you have streaming algorithms that are correct at all points in the stream. With a memory that beats this naive, just repeat the algorithm log n times and take the median. Right? I described this earlier in the talk. So there are many algorithms that have memory that is better than that. These are called strong trackers. So they're sort of, they track the output at every point in time and they get good memory. And sketch switching is particularly useful here. But related to that, computation paths is also useful when you have a space complexity of your streaming algorithm that has a dependence on the failure probability that is better than just multiplying the space by log 1 over delta. Okay, so these two methods are related to each other, and so if I have an algorithm, which maybe has a space complexity of something like 1 over epsilon squared. Log 1 over delta plus log 1 over delta or something. Like if I can somehow separate out the failure probability dependence from multiplying the entire space, computation paths is a technique that can exploit that. So okay, at this point, it's high level. The point is just that these two transformations are good in different regimes for the underlying streaming algorithm. So let me just say more about this. Okay, so in order to define the guarantees, we need the notion of what I'm going to call the flip number. Okay, so for a function f from n-dimensional vectors, like your underlying streaming vector, to the reals, we define the epsilon flip number, lambda sub epsilon of f, to be the maximum number of times your function value can change by a factor of 1 plus epsilon after poly n updates. Okay, what does this mean? I start maybe with, so suppose I'm doing f2 and my initial vector x is 0, then my function value is 0. I have integer updates, so then my next function value is maybe 1. And then it's going to keep growing if I'm in the insertion only model. And every time it changes by a multiplicative factor of 1 plus epsilon, then I add 1 to my flip number. Okay, so the flip number is how many times can my function value grow by 1 plus epsilon multiplicatively. And in the insertion only model, the flip number for many problems is just order log n over epsilon. Okay, so here's the example. The function is the p norm to the p. That's just the sum of p powers of absolute values of entries of your vector. And if you're in an insertion only stream where the updates are bounded by poly n and you have poly n updates, then your initial value is 0 if your vector x is 0. And after poly n updates, it's at most poly n. So your flip number is log base 1 plus epsilon of poly n, which is just log n over epsilon. Okay, so the flip number is not a very large quantity, 1 over epsilon log n.
Quick question, David. So yeah, it's a delta t dependent thing, right? So it's just an upper bound on delta that you are allowed. Log of delta in some sense.
Yeah, so I'm assuming a stream length at most poly n, and I'm assuming that my updates delta t are at most poly n.
Oh, yeah.
And that's why I'm taking log of poly. Yeah, that's right. If you have longer streams, then this log is of the stream length. Yeah.
Like if I don't bound the update, so if I don't bound the delta, then it could be large, right?
Oh, that's right. Yeah, I mean, if my delta is exponential in n, then maybe I double every single update, right? And then my flip number could be n. Yeah. So you do need a stream length that and a delta that are polynomially bounded. Yeah.
Okay.
Okay, so that's the flip number. And given that, I can state our main results with these transformations. So the first is the sketch switching result. So this is sketch switching. And what it says is let A be any algorithm which epsilon tracks some function. Okay, so it's correct with within 1 plus or minus epsilon at every time step. Then there's a robust algorithm, A prime, which is also correct at every time step, where the space is the space of the original non-robust algorithm times the flip number. Okay, so the space blow up is flip number. And here is this other computation paths result. Computation paths. And what it says is, you give me any streaming algorithm A. Again, it tracks some function at every time. And suppose it uses space A comma delta. Okay, so I'm parameterizing it in terms of its failure probability delta. Then there is a robust algorithm A prime that uses space A comma delta prime, where delta prime is now much smaller. It's delta times n to the minus flip number. Okay, so what the second result is saying is, give me any streaming algorithm A and just set the failure probability delta to be small enough, and you get a robust algorithm. Okay, now the failure probability becomes n to the minus flip number. For a lot of these problems, I said they have a log 1 over delta dependence. When I take the log of this, I'm going to get roughly flip number blow up in space again. Okay, so these results are comparable, but not exactly the same. So you should think of this as roughly the space blowing up by the flip number. Okay, so yeah, let me discuss the intuition and the transformations, how they work, and the intuition behind their correctness. So here I've just repeated the theorem statement for the sketch switching result. The idea behind this result is we're going to keep roughly flip number of independent sketches of the underlying vector x. Okay, so we have this vector x, and there's some non-robust algorithm A, which might just sketch that vector. Okay, and what we're going to do is we're going to take a bunch of independent sketches. They're all going to be initialized at the beginning of the stream. Okay, they start from the beginning of time. But we're only going to pay attention to certain ones at a given time. Okay, so I'll describe what this means. The number of sketches we take, again, is roughly flip number. Okay, so here is the way it works. Okay, so the whole algorithm is here. Let's go through this slowly. So as I said, we have roughly flip number of independent sketches. Okay, S1 through Sk. K is this value. And each one of these is a good tracker. Okay, so it provides a 1 plus or minus theta epsilon approximation at any point in time for a fixed non-adaptively chosen stream. Okay, so these are good sketches for non-adaptive streams. Now, what do? We're going to set I equals 1. What that means is we're going to start looking at the first sketch. Okay, all of these are going to be updated every single time step, but we're going to pay particular attention to the first sketch right now. And we're going to set our initial response to be 0, which is just consistent with a lot of these functions. When you evaluate them on the 0 vector, they give you 0. Okay. And here's how it's going to work. At a given time t, we're currently monitoring Si. Okay, I starts out as being 1. What does that mean? Well, we look at the estimate that Si provides us, and we check ourselves, is that estimate close to the previous response that we output, the response that we output at time t minus 1? Okay, so is our estimate provided by Si within 1 plus or minus epsilon over 3 of the previous response? Okay, if it's not, then we're in trouble. We can't use the previous response because hey, the function value might have changed a lot. So what we're going to do is we're going to set our new response at time t to be the estimate provided by the ith sketch. But then now we're in trouble because we've told the adversary something about our sketch, SI. And who knows what that reveals? It could reveal everything about SI depending on the sketch. So what we're going to do is we're going to throw out SI. We're never going to use it again. We stop monitoring it, and that's it. We replace I with I plus 1, and now we're going to start monitoring the next sketch. Okay. Now it might be the case that your estimate of SI was within 1 plus or minus epsilon over 3 of the previous response. In that case, you're just going to set your new response at time t to be equal to your old response at time t minus 1. Okay, now this is kind of a good thing to do intuitively because you're not using the output of the sketch, SI, to produce your new response. You're just piggybacking off of your old response, RT minus 1, which was provided by some previous sketch before you threw it away. Okay, so the adversary doesn't see any outputs of the ith sketch until it's too late. Like once it sees an output of the ith sketch, then you immediately throw away using that sketch in the future. Okay, so let's try to think about why this works. Okay, so first of all, so here is a rough proof of correctness. We have this two-player game between adversary and the streaming algorithm. And the adversary's job is to try to make the streaming algorithm fail at some point in time. And so it tosses random coins. But if the adversary succeeds, then by averaging, there's some good fixing of its random coins, which succeeds. Okay, so that means actually without loss of generality, we can assume that the adversary is deterministic. Right? Because if we prove that we have a robust streaming algorithm for deterministic adversaries, then we also get one for randomized adversaries. Because if you have a good randomized adversary, you can fix its randomness. Okay, so now if you have a deterministic adversary, though, well, this importantly fixes the part of the stream the adversary is going to give to the ith sketch after SI minus 1, the previous sketch, returns its answer out. Okay, so suppose that you were monitoring SI minus 1 and you're using SI minus 1 and you're returning the answer out. Okay, now you're monitoring SI at this point. Okay, because SI minus 1 is, say, no longer useful. You already posted its output out and you threw it away. Okay, now what's happening is the adversary is seeing a bunch of responses. It's seeing out, 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 out. It's just seeing the same value over and over again. Right? Because until you decide to use the output of SI to change your response, the adversary just sees this list of responses over and over again, out, 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 out. Which means that we can think of, we have a deterministic adversary that's just seeing a list of all these responses out. And so it chooses some deterministic stream. Okay, so that's what I mean by this fixes the part of the stream the adversary gives to the ith sketch after the previous sketch was thrown away and it returned its answer. Okay, because the adversary is not seeing anything new about this new sketch, SI. It's just seeing, the same output, out, 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 over and over again. And since SI itself is a good non-adaptive sketch, whatever deterministic stream that the adversary chooses here, given that seeing this response over and over again, we know that SI is with good probability good on that stream. Okay, so let me say it in more slowly here in bullets. The important point is the stream does not depend on SI. Okay, so the the adversary, it's learning something, right? Like if it keeps seeing out over and over again, then it means that the estimate that SI is producing is within 1 plus or minus epsilon over 3 of the previous value out, because we didn't post anything new. Sure, it's learning something new about SI, but we can fix the stream it creates that it feeds to SI beforehand, because the stream it creates is just based on seeing these responses out forever. Okay, and so whatever stream this deterministic adversary creates based on these responses, we just say that SI is correct on that stream with good probability. Okay, I do want to stress that the stream, it might depend on all the previous sketches, but that doesn't matter. Those have been thrown away at this point. It doesn't depend on the next sketch. And so this new sketch SI is correct at all positions in this new stream. Okay, it's a little bit tricky of an argument, right? The adversary is learning that SI's estimate is close to out, but it doesn't matter because it fixes, it can, without loss of generality, fix its stream beforehand, where it just sees responses out forever. Okay, yeah, so as I said, SI continues to output this old value out until its value out prime is not within 1 plus or minus epsilon over 3 of the old value, at which point we post out prime and we throw away SI and we start monitoring SI plus 1. Okay. Yeah, and as I said, you might worry you learn something about SI until it outputs out prime. And you do, you learn the fact that its estimates are close to out. But the stream that it's fed is fixed, can be fixed beforehand. So SI is correct on whatever fixed stream you choose until SI outputs out prime. So that's the argument of correctness. Are there any questions there?
So is there any lower bounds that this extra factor, what do you call this factor? This,
the flip number, yeah.
Flip number, yes. That this dependency is needed.
So I'm going to get to a discussion of that in this talk. So yeah.
Yes.
Sure. Okay, so that's the correctness, but you might worry, what if I run out of sketches? I only initialize with flip number of sketches. And the way that you can argue that you never run out of sketches is that if your sketch provides a 1 plus or minus theta epsilon approximation, and here you need some epsilon twiddling, which is important to make this work out. Then if the output of your SI out prime is really not close to the old output, then it means that necessarily the function value actually had to change by some amount, 1 plus or minus epsilon over 12, right? If you have a good approximation to the underlying function and out prime was also a good approximation, out was a good approximation and out prime is different, then it means, something had to change, the actual function value changed. But importantly, that means that if f changed by this factor, you can charge it to the flip number, okay? Which is why we only need, flip number of sketches. We'll never run out of sketches. And conversely, for correctness, if the function f actually does change by a 1 plus epsilon factor, then you can show that necessarily the new estimate has to be far away from the old output, just for correct. So you're correct at all times. Okay, so this can be shown just by using correctness of the non-adaptive streaming algorithm. Okay. So that's the idea behind the sketch switching transformation. As you noted, it blows up the space by a flip number factor. Let me also talk about this other method that I mentioned called computation paths. And the idea is similar to sketch switching. The idea is instead of using multiple independent sketches, you're just going to use one sketch. And you're going to monitor yourself. You're going to be looking at your sketch and you're going to be asking, can I continue to output the same thing I output at the previous time? And I'm looking at the new estimate my sketch is providing at the new time. And provided it's close enough to the old output, then I'm just going to keep outputting the old output. And the reason for doing this means that your output doesn't change that many times during the stream. Because you're only changing your output when you absolutely have to, meaning like your old output is no longer a valid 1 plus or minus epsilon approximation. And if you only change it when you absolutely have to, then it kind of means you only change it roughly flip number of times. And this in turn kind of means that, well, if I have a stream of length poly n, there aren't that many deterministic streams that the adversary could create, because there are only a small number of times at which the output actually changes. Okay, so this is the intuition, and let me just formalize it. So the theorem statement is repeated. It just means, take your non-adaptive algorithm and replace it with a much smaller failure probability, and now you get a robust algorithm. And here is the proof. So streaming algorithms can be made robust by setting the failure probability delta prime to be delta times n to the minus flip number. And the idea is, I'm monitoring myself as a sketch, and I'm only going to change the output flip number of times, okay, when I absolutely have to. And the stream is of length poly n. And I'm going to assume that the output of my streaming algorithm is log n bits. Okay, so how many possible streams can a deterministic adversary create? Well, at the very beginning, it creates some stream. If it just sees the output 0 forever, it would create some fixed deterministic stream. Okay, but at some point, you can't output 0. You have to output something else because the actual function value changed. Maybe, you change at this point in the stream. Then the adversary says, okay, the output changed, so I'm going to create this new deterministic stream. And then, you keep outputting the same value you did, but then at some point you can't because the function value changed. So you output something new here. And then the adversary says, okay, I'm going to create this new deterministic stream. And so the point is, well, how many paths, this is why it's called computation paths, sort of how many paths are there here? Well, the stream length is poly n. Okay, so the location where the first time the output changed, there are poly n choices for that. And then there are poly n choices for the location in the stream where you have to change the output again, and then poly n choices again. So there are poly n to the flip number. Let me just write lambda, poly n to the flip number possible locations in the stream where you output something new. And each time you output something, it's log n bits by assumption. So there are only poly n choices for an output, and you have lambda outputs. So in total, this is n to the order flip number possible computation paths the adversary can create. And so if I just set my failure probability small enough, I can union bound over all of them, and I'm correct on all of them. Okay. So that's the whole idea. And yeah. Any questions about that? Okay. Yeah, so you can instantiate these transformations with many different streaming algorithms. Okay, so in this original paper, we looked at insertion-only streams. So the flip number was 1 over epsilon log n. And if you see so here's the problem: distinct elements, FP estimation, heavy hitters, entropy. You may have heard of some of these. There's a non-adversarial bound here. Here's the space bound. I'm not going to detail these. And there's an adversarial bound. And the rough takeaway is that the adversarial bound more or less blows up the space by a 1 over epsilon factor. Okay, it's actually 1 over epsilon log n, but you can do some tricks. But you can't really avoid this 1 over epsilon blow up, which is coming from the flip number. Okay, so that was what we had originally. Some of these results come from computation paths, some come from sketch switching. It just depends on the underlying streaming algorithm. And yeah, so going back to Barna's question, do we really need to pay this overhead? And there's been a lot of follow-up work to this, and I want to go over some of this in detail. So the first improvement to this used a beautiful connection to differential privacy by Hasidim, Kaplan, Mansour, Matthias, and Stemmer. And by using differential privacy, they're able to beat this slip number blowup. I do want to say that there was some earlier work we had with Hart that was not in the streaming model, but which is in a linear sketch model, where we had adaptive queries where also differential privacy was useful. But this was sort of the first use of it in streaming, and they were able to use this differential privacy to improve these roughly 1/epsilon cube dependencies to 1/epsilon to the 2.5. Okay, for many of these classic problems like estimating distinct elements, F2 estimation, and so on. The technique they used, gives something very general, that instead of getting flip number blowup, you get square root flip number blowup. Let me just say that this technique is useful not only in the streaming setting, but Bimol and Kaplan, Mansour, Nissim, Sarenarak, and Stemmer also use this idea in the dynamic model. Okay, so the idea is quite powerful. What it is differentially private median estimation. So what does this mean? So, roughly speaking, what do we do in sketch switching, for example? We had a bunch of independent sketches, right? We had like S1 times X, S2 times X. I'm just thinking of this as the sketch being matrix vector multiplication, like it was in our example. So we had like roughly flip number of these, right? Independent sketches. Sorry, let me put lambda here. Flip number independent sketches. We said, okay, this sketch is bad, so we're going to throw it away. We're running all of them in the background, but we're monitoring one at a time. And we walk through all flip number of them potentially in the stream. And what this differential privacy idea says, it says, hey, wait, you know what I'm going to do? I'm only going to use square root flip number of these sketches. And what I'm going to do is I'm going to use a differentially, I'm going to output, what I can do is try to output the median of each of the estimates provided by these sketches. Okay, so, we know that median is a way of reducing failure probability. I can try to output the median of all these sketches. And if I do it using a differentially private mechanism, it turns out that, with square root lambda sketches, you can handle lambda changes to the function value. Okay, so this is a very cool idea. And, in these follow-up works, it takes the form of something where you have a data structure where if the data structure has size Q, you can handle roughly Q squared queries to the data structure, Q squared adaptive queries. Okay, and so it was used for a number of graph problems, shortest path problems, and cut problems in this work. So very general technique. But for these streaming problems of F0 and F2, you might still ask, well, is 1/epsilon to the 2.5 the limit? Using a different technique in work with Joe, what we showed is that actually you can get 1/epsilon squared. Okay, so there actually is no overhead for many of these streaming problems in insertion-only streams. Okay, we used a new notion called difference estimators in a stream. So let me talk about that a little bit. I should note that this doesn't use differential privacy. It's sort of more tailored to improving these streaming bounds, getting tight bounds for this. Differential privacy, although it doesn't get the tight bounds here, is it's useful for all these other models as well.
David, one question in the previous slide, you mentioned dynamic models. So, like, what does it refer to? Like, it's
like you might have both update time to a data structure, and you might also have query time. So you can imagine, maybe for regression, maybe you're maintaining some sketch and you want to query it, and so it refers to those.
Okay.
Thank you. Sure. So we introduced these difference estimators, and what is yeah, and just saying what the result is, we improve these 1 over epsilon cubed and 1 over epsilon with the 2.5 bounds to roughly, to 1 over epsilon squared up to log factors. And this 1 over epsilon squared is actually optimal. Okay, so non-robust streaming algorithms for these problems require 1 over epsilon squared bits. So many cases they match, even the logs match. In other cases, the logs are open, so there are still questions here. And these difference estimators, they do actually have applications to other streaming models. In particular, the sliding window model is a streaming model where you only look at the most recent n updates, for example, in your stream. And difference estimators sort of naturally fit into that model and give you tighter bounds for norm estimation in that model. I won't get into the details of that, but let me just tell you a little bit about difference estimators. So the sort of motivating question is, do we really need to switch our sketch whenever the output changes by a 1 plus epsilon factor? Like, do we really need a brand new 1 plus epsilon approximation? And the answer, is maybe it's sort of unclear what the adversary is learning, right? I mean, you could imagine really horrible sketches which encode all of their random bits into their least significant bits of their output just because they want to be really bad sketches, right? And then, it would be completely destroyed. So, it kind of depends. What is the adversary learning? But sort of the question that drove this work is, if the last output out was a 1 plus or minus epsilon approximation to some function value f, and then f changes to f of x prime, where f of x prime is not that different than f of x. Okay, so maybe you're in the insertion only model and it grows by a 1 plus epsilon factor. Then, yeah, do you really need a brand new 1 plus or minus epsilon approximation to the new function value? Do you need a sketch providing that? And it seems wasteful, right? Because you've already fixed out. You've told the adversary, hey, at this previous time, out was a 1 plus or minus epsilon approximation to the function value. Okay, so here's f of x, and here's out. And out is a 1 plus or minus epsilon approximation. And at some future time, I have f of x prime. Okay, I'm in the insertion only model, so x prime, is only getting, updates, positive updates to coordinates in x. And so, I want to output some new out prime here. But maybe instead of using a brand new sketch to compute this, what I could do is I could output my old value out plus an estimate to the difference f of x prime minus f of x. Okay, now if I knew the difference exactly, then I would have my nice new 1 plus epsilon approximation at my new time step. And you might say, well, maybe this doesn't buy you anything because, hey, I have to approximate f of x really well, and I have to approximate f of x prime really well so that I can take the difference and then get a good estimate to the difference. But that's not necessarily the case, right? Maybe I can approximate this difference very well without approximating these individual quantities very well. And the point is that this difference is very small, right? It's like order epsilon f of x, the actual difference. And so I don't need to approximate the difference very well either. And so that's what we take advantage of. So we design the first difference estimators to approximate differences for a number of streaming problems, and we are able to add it to out. And by combining these in sort of a binary tree scheme with different granularities, you can show how to use this to get a 1 over epsilon squared dependence. That's all I'll say about that. Yeah, let me just mention a number of other follow-up works. So this idea that we used with difference estimators, I said we didn't use differential privacy. So there was a nice follow-up work that combined the idea of difference estimators with differential privacy. And the idea with the difference estimators is the dependence on the flip number we got was roughly epsilon times lambda. I didn't say why, but if you remember, okay, the first work, you needed lambda sketches, right? That's what I said. Lambda sketches was the very first work. And then I said using dp, you can get square root lambda. dp. Yeah, and then actually using our difference estimator, we can get this, okay? And it turns out that actually, since lambda is so darn small in like an insertion only stream, epsilon times lambda is like 1 over epsilon. So epsilon times lambda is actually like a constant. It's actually better than square root lambda, which is square root 1 over epsilon. But you know, it's specific to insertion only streams. And so what these guys did in this nice follow-up work is they combined the best of differential privacy and difference estimators. They got square root of epsilon lambda. Okay, they needed a slightly different notion than flip number called the twist number, but I'm not going to get into that. There's also a nice work of Ben Eliezer, Eden, and Onak, which shows how to beat this square root flip number bound in turnstile streams, where the updates delta t, they're restricted to be in like 1 minus 1. Okay, so it means that like intuitively, if I'm at some function value, it's going to take a lot of updates to change to some other function value, because I can only change by 1 at each step. And so it takes a long time. And using the fact that it takes a long time, you can combine sort of a deterministic algorithm when the function value is small with a sketch switching approach when the function value is large. Anyway, if you balance things appropriately, you can beat the square root flip number dependence. For, sorry, what this means is this is for FP estimation, okay, FP moment estimation. And instead of getting square root flip number, you get flip number to the 1/2 minus a function of P. Okay, now there are some separations though. So going back to the question earlier, there's a very nice result of Kaplan, Mansour, Neeson, and Stemmer, which shows that actually there is a problem. You know, maybe it's not your favorite problem. It's not FP moment estimation, but there is a problem in the insertion only model for which any adversarially robust algorithm does require a blow up of square root flip number over the non-robust algorithm. And you know, in fact, if you set parameters appropriately, you get an exponential separation in memory for robust and non-robust algorithms. So that's a very nice result. Again, the problem might be a little bit, I mean, it's very nice. The problem is not sort of a well-studied streaming problem. There's also work that looks at separations for sort of problems that are studied in the stream. One of them is a graph coloring problem, where you have some bound on the max degree and you want to color your graph. And you can show that, you know, robust algorithms, if they want sublinear space, need to use a lot more colors than the non-robust algorithms. So there's a nice separation there of Chakrabarty et al. Another direction here is robustness of classical algorithms. Okay, so you know, maybe you're not interested in designing a new algorithm because you have all this code, you know, in your company. You know, you have all this code that's using CountSketch, right? You don't want a new heavy hitters algorithm. You want CountSketch to be robust. And so there's this line of work saying, you know, can I just look at classical algorithms and determine if they're robust or not, or maybe slightly change them so they're robust. And in work of Cohen et al., they show that this CountSketch algorithm, which is an algorithm for finding heavy elements, frequent elements in a stream, is not robust, but it can still handle a quadratic number of queries in the sketch size. So if I have a sketch size of S, it can handle S squared queries before its randomness is compromised. But you have to slightly tweak the estimator. It's not the usual estimator. But the sketch is the same. And in follow-up work of Cohen et al., they show that this quadratic dependence, this blow-up is inherent for a large class of estimators, that you really can't tolerate more queries. Okay, and I'm almost done. Let me just say that there is other recent work that looks at the sort of what's called the white box model, with work with Aitai et al., where here the model is the adversary has even more power. It not only does it see your responses, it sees your entire state. And so you might be worried at this point, you might not be able to do anything. One thing is, yeah, so the adversary can see the internal state of the streaming algorithm, but the streaming algorithm still gets new fresh randomness on each update. Okay, so it's not, it still has a little bit of power. It gets some new randomness at each time step. And it turns out that this is quite useful, and I don't have time to tell you about it, and I'm just going to say what's in red here. If you make cryptographic assumptions, okay, if you assume your adversary has polynomial time, and you make cryptographic assumptions, you can actually do things that you can't do deterministically. So you can get low memory for a number of problems. You get trade-offs for number of distinct elements and finding heavy hitters under cryptographic assumptions. There's also some work on linear algebra problems. So things like subspace approximation and regression. I won't say more about that. And let me just conclude and mention some open questions. So this is a new area. There are many other works in progress I didn't have time to discuss that I hope the other speakers in this series discuss. The natural question is, for many problems, we don't have tight bounds or maybe any bounds for streaming algorithms that are adversarially robust. Okay, so you can take your favorite graph problem or optimization problem in a stream, try to make it robust. And yeah, basic questions are still open. Okay, so for this F2 problem that was our running example, if I have positive and negative updates, that's called a turnstile stream. It's unknown if polylogarithmic space suffices or if there's a poly-n lower bound. Okay, now if I have a turnstile stream, I can like add something and subtract something and do it over and over again. And I can make my flip number huge, like poly-n. So you might say, hey, I told you there's a root flip number lower bound, but that was for an artificial, that was for some problem, right? It wasn't for F2 problem, the F2 problem. So maybe for the F2 problem, you can do better. As I mentioned briefly just now, for the white box model and cryptographic assumptions, hey, here anything could be possible. Maybe with the right cryptographic assumptions, you can, get any, have no overhead over any streaming, no non-robust streaming algorithm. There are also questions about the model. So should the adversary have unlimited power? Should it be polynomially bounded in time? Maybe it has a little bit more memory than the streaming algorithm. There are lots of different models you could think about here. I think those are interesting. So let me just stop there. And yeah, thanks a lot.
Thanks, everyone. Thanks, David. Are there any questions? So, does the difference estimator assume that the streaming algorithm has a linear sketch, or doesn't really?
No, it doesn't need a linear sketch. The difference estimator is just a way. If you have some function value at some time t, what you'd like is to be able to produce an estimate to the difference at some future time. So, many of these are linear sketches, but there's no reason they have to be. Maybe just to give you a quick example, because maybe this is too abstract. Like if I suppose I have some x, and at some later time in the stream, I have some underlying vector x prime, right? I'd like to estimate the difference in, say, squared 2 norms, right? This would be the difference estimator for F2. You can actually write this using Pythagorean theorem as the squared 2 norm of x minus, let me write it as x prime minus x. It's the same thing, but x prime, the coordinates in x prime are only larger than those in x because it was an insertion stream. Plus like the dot product of x prime and x. And so the important thing is if I want to estimate this difference, I just need to estimate this quantity and this quantity. And the point is, since x prime is so close to x, because we're assuming the function value didn't change that much, this quantity here is very small. So I don't need a very accurate estimate to it. And this dot product is also very small, so I don't need a very accurate estimate to it. So it's possible to estimate this square difference without actually estimating each of these individual quantities very large. Yeah. So, but for your question, yeah, there's no reason this, and for things like F0, we we didn't have a linear sketch. So there, we have some difference estimators that don't use linear sketches.
Okay.
Are there other questions? It was a very nice talk, David, and it also set the platform very well for like future talks for in this series. So thank you a lot.
Thanks.
Great. Okay, let's thank the speaker once again. And I hope to see you all in the future series.
Yes, and you will hear about some of these areas that David mentioned in the future talks. So thank you again, David, for giving the presentation today.
Okay, thanks everyone. Bye-bye.
Thank you.